Double replacement reactions are sometimes also referred to as metathesis reactions. Not in our book, but other books, so be prepared for that change in terminology. Here's an example of a very typical double replacement reaction. Aqueous solutions, that indicates both solutions are aqueous, of magnesium chloride and silver nitrate. So here we go. Magnesium chloride. It's a solution containing magnesium ions and chloride ions that are together, and a solution of silver nitrate, AgNO3, aqueous. Now this question is different than the last ones we've been doing, because now we have a compound plus a compound, and that should scream at us, these are both ionic, that we're going to make a double replacement. We're going to take our magnesium and our silver, and we're going to switch partners. Now to do this, we need to know the charges of all of our ions, and we do. So magnesium, and it's okay again to have a working step. You shouldn't necessarily be able to do all this in your head quite yet. Magnesium's a 2+, and the nitrate is a 1-. So you need to have Mg in a bracket and O3 taken twice. The state you need to know, and all nitrates are always going to be soluble in a water environment. The second product is silver with chloride. Silver's a 1+, chloride's a 1-. If you go to your solubility table, you will see that silver chloride is in fact insoluble in a water environment, meaning it cannot break apart. It will precipitate, and that is a solid. Now, one thing I haven't told you before, this is a new skill, is that when, as a result of crisscrossing your partners in a double replacement reaction, if you do not produce a solid precipitate, or a liquid like water, or a gas, then the reaction will not happen. You would basically be adding 2 beakers of nondescript liquids together, and you would see nothing happen. There would be no color change, there would be no precipitate, there would be no heat, there would be nothing. So you have to remember, if your products do not produce a precipitate, the reaction will not happen. If the reaction doesn't happen, then of course you would write simply no reaction, and you wouldn't balance it, because it couldn't actually happen. I'm going to balance the equation. I'm going to teach you another skill. So I have 2 nitrates on the right, I need 2 on the left. That gives me 2 silvers. So I need to have a 2 in front of the silver chloride, and that reaction is now balanced. Although I probably will not ask you to do this, I'm going to show it to you anyway because it's very important. What's called the complete ionic equation. You will be asked questions about this procedure without actually having to do it all. It's very simple, actually. The first reaction, I have magnesium and I have chloride together. Although we're writing it together as a compound, you need to be aware that in that solution there's actually magnesium ions that are floating around freely and chloride ions floating around freely. And when you look at the subscripts that were used to crisscross, we can write the complete ionic equation. It's quite long, and we have to go across the page and keep going. So magnesium's a 2+, and that's free floating in the water, so it's aqueous. The chloride ions are a 1-. They are again aqueous, but the difference is there's 2 of them. When I break it apart, when you crisscrossed, that 2 was included to crisscross. So there's 2 chloride ions, and now in that second beaker that it got added to it, I now have 2 silver ions that are free-floating and aqueous. And I have 2 nitrate ions that are free-floating and aqueous. And as a consequence, when they come together and they hit each other, these 2 ions, when they collide, will make a precipitate. The other ions stay aqueous. So therefore, you're going to have magnesium as a 2+, which is aqueous. You're going to have, keep going across the page if you have room, 2 nitrates that are aqueous. And you're going to have the AgCl, which is a solid which does not split apart, and that stays together as a unit. And that's a complete ionic equation. I'm going to highlight the precipitate. Precipitate is the 2 silver chlorides. What made that compound was the fact that I had 2 silver ions from one beaker reacting with the 2 chloride ions from the other beaker, and they came together and made the product. What you should notice here in this reaction is that the magnesium and the nitrate are quite useless. They are exactly the same on the left-hand side and the right-hand side of the equation. Nothing has changed. So when you do the net ionic equation, you cancel whatever didn't change. And those substances that don't change are called spectator ions. Think about it this way. If you went to a football game and you were sitting up in the stands, as a spectator you don't do anything. You are the magnesium and the nitrate that are observing the reaction. The reaction is the silver and the chloride down the field. So the spectators get canceled from the complete ionic equation when you go to write the net ionic equation. And what's left, and the order doesn't really matter. I could write it 2 Cl's and 2 He's. Might be more reasonable to write it as 2 silver ions that are aqueous react with 2 chloride ions that are aqueous, and they come together to make 2 silver chlorides that are solids. And then if you're thinking ahead to basic math skills, the 2's can all reduce, and you would get pretty much for every 1 silver ion that's in solution, AQ, you need 1 chloride ion in solution to produce 1 silver chloride formula unit as a solid. And that last one is your net ionic equation, your final net ionic equation. So remember, you can only have a double replacement if you produce a solid or a liquid or a gas. And otherwise, it will not happen. And I want you to think about this. The ions that are not going together to make the product, which is the solid, or the ions that remain in solution as the aqueous, these are called the spectator ions. They don't do anything. And the spectator ions in this question were the nitrates and the magnesiums. The important ions were the silvers and the chlorides. Spectators were the nitrates and the magnesiums. Useless. Question 2 on the next page of your booklet, I changed it for 2 reasons. One, it was a bad question. It should have said aqueous solutions of, so add that to your notes, aqueous solutions of, and I changed the other reactant, sodium carbonate reacting with nitric acid. To show you something unique that you wouldn't get from the example I provided. Okay, sodium carbonate. Sodium's a 1 plus, carbonate's a 2 minus. So sodium carbonate is Na2CO3. Although it wasn't given the question, I've now said these are both aqueous solutions, so I'm going to put AQ. If this reacts with nitric acid, now an ic was an 8, so a nitrate is NO3. Therefore, HNO3 is the correct formula for nitric acid. When these react, it is a compound-compound situation. You're going to see a double replacement where the cations are going to each replace, and you are going to get the following product. You are going to get the Na with the NO3, sodium with nitrate, and that is a very common aqueous solution. All nitrates are soluble, and all group 1 ions are soluble. You're going to get, for the other product, the hydrogen with the carbonate. Well, hydrogen's a 1 plus, and carbonate's a 2 minus. So you actually get H2CO3. H2CO3. Because this compound is an acid, we would normally write it with a typical acid state of aqueous. But what you may not know about this acid is it's very unstable. Consequently, that acid breaks down almost immediately to give you two very common compounds. I'm going to rewrite it underneath this with what you get. So the sodium nitrate is your first product or typical product, and the sodium carbonate, the hydrogen carbonate, as an acid, carbonic acid, breaks down to give you water as a liquid and CO2 as a gas. Otherwise, this reaction wouldn't happen because two aqueous products don't fit the bill for double replacement. This is one of those little facts you have to add to your memory bank, that carbonic acid, H2CO3, it's made in POP, okay, it breaks down immediately to give you water and carbon dioxide. And because water is a liquid and carbon dioxide is a gas, then that fits the bill and it will proceed as a double replacement. The equation is not balanced because you have two sodiums on the left. You need two on the right. So 2 in front of the NaNO3. That gives you two NAs, two NO3s. So you need 2 in front of the HNO3, and that gives you 2 H's. It's actually easier to balance in this format than the second one, but the second one on the product side is reality. And you need to be aware, in case you receive that on a test question, I could say, what does the unstable carbonic acid break down to give? And I would hope that you would know you get carbon dioxide and water. In terms of spectators, well, if the H2 and the CO3 are what we would call the driving force, the big cheese, the big result, then it's quite easy to tell that the things that make those are the H's and the carbonates, and the sodiums and the nitrates would be the spectators. They're quite irrelevant to the reaction. They remain aqueous. So sodium as an ion and nitrate as an ion, those two would be considered spectator ions. not all that important. Okay, third example. We have an acid and a base. We know it's an acid because it says it's an acid. We know it's a base because it has the word aqueous in the front. This is actually a very common reaction and quite important that you understand the parts. So hydrochloric acid, that one I'm sure you have memorized by now. HCl is an aqueous. Aqueous sodium hydroxide. NaOH as an aqueous solution. So there's a base. Turns litmus blue, would have a pH greater than 7, would taste bitter. The acid would have a pH less than 7. It would turn litmus red. It would taste tart or sour. All those factors we studied in chapter 6. When these come together, you do a double replacement. You will get NaCl, 1 plus 1 minus, and salt is of course soluble. And you will get for the other product HOH, which we know to be water. And because we've produced a solid or liquid or a gas, this reaction will indeed happen. In terms of generally speaking, this is what happens when you mix together an acid and a base. You get a salt, which is basically an ionic compound, and you get water. The salt's quite irrelevant in the reaction. The driving force is to make the water, to make it neutralize. So what we could eliminate in terms of spectators is that the water is the driving force and the water is HOH. Then the OH from the base and the hydrogen from the acid, those are the two things that are most important. And the anion and the cation from the acid and the base are spectators. So H from the acid, the OH from the base, they react together to give you the neutral water. And this reaction, although it's definitely a double replacement, is quite often referred to as a neutralization reaction because it can neutralize your acid and your base. Now mind you, the acid and base would have to have concentrations and volumes that would make those acids and bases neutralize, but hypothetically speaking, if you had 1 mole of each, then your reaction would be neutralized. Spectators would be the sodium and the chloride. They are not useful for this reaction. Necessary, but not really useful. And last but not least, in your booklet there's an example of barium hydroxide with phosphoric acid. The question is not worded very well. I would ask that you add the word aqueous to the front of the barium hydroxide, because then that compound is not a solid, but it's actually a base. So, as an example of a harder one to balance, barium is a 2 plus, hydroxide's a 1 minus, so it's Ba bracket OH2, and it's aqueous. Phosphoric acid, ic was an 8, phosphate's PO4 with a 3 minus, so it's H3PO4AQ. We have an acid and a base. We have a compound, double replacement. The H is going to go together with the OH, and we're going to get the water. Write it as HOH or write it as H2O. Definitely balance it as HOH, but the key is noticing that it's a liquid. And therefore, in the minute you make a liquid, or a solid or a gas, you have the criteria to be a double replacement. The other product will be the barium with the phosphate. And barium is a 2 plus, and phosphate is a 3 minus. Put them together, you get Ba3 bracket, PO4 taken twice, and on your solubility table, you will note that the only phosphates that are soluble are group 1s and ammonium. Barium's a group 2, so there's your solid. So in fact, in this reaction, we've made 2 products that are not going to break apart They're going to stay together, and therefore there are no spectators. Every ion in this case is useful. To balance it, though, we need to make sure everything is even left and right, and this is the most complicated part of the reaction. 3 bariums, I need 3 on the left. 2 phosphates, I need 2 on the left. That gives me 6 OHs in the barium hydroxide and 6 H's in the acid, which is why I need to put a 6 in front of the H2O or the HOH. 3, 2, 1, 6 to balance. Double replacements, you've got to make a solid or a liquid or a gas. Liquid commonly would be water. A gas, something like carbon dioxide. The solid is a precipitate. You want to go to your solubility table and combine your 2 ions and see which one is a precipitate. A gas, you might get, I guess, CO2. Okay? If, when you balance your reaction, you get an AQ with an AQ, and you get another AQ on the right, and another AQ, that is no reaction. Okay, that's a no reaction scenario, and there's no point in balancing it because it won't happen. So you want to always look for your precipitate before you start to make sure you're not being tricked, so to speak. Double replacements.